Before I make a decision as to which section to tackle next, I was thinking what kind of test could I try? The fact that I couldn't find much of the 125 kHz on the power or input to the MOSFET power modules really made me look at the common ground connection a bit closer. My overall layout is like this. The source circuit of the power MOSFET does not connect to ground on the MOSFET power module. The common ground connection is at a bus bar the main current shunt connects to. So when I made this modification of removing this amp, there is quite a bit of wiring between where the current is sensed, the source terminal of the power MOSFET, and common ground. So I'm going to try and reposition common ground as a test. So I will connect this net to ground on the MOSFET module, which really won't be difficult. As can see with the module unplugged, there is no connection between the module ground and the source load terminal. I'll scrape off some solder mask. Not going to worry too much about messing up the PC board. These are going to have to get replaced, I'm sure of that. I just don't want to damage the MOSFET. They're getting close to $40 a piece now. I'll just solder a jumper from the source load terminal to the ground. Of course, now the common ground point will be on the main control board, and maybe that is where it should be, but that will create problems of its own. I will disconnect this, try to eliminate any extra ground loops, and run a few tests, see what I get. This is the AC coupled signal at the load terminals connected to a 600 watt linear power supply. This is at a 2 amp load, and it really looks pretty good. Compared to this waveform, which is the same 2 amp load but before the ground modification, here really shows a difference. The green waveform is the modified ground. The purple waveform is with the unmodified ground. That's a lot of difference. Probably 350 millivolts of a 125 kHz sine wave, whereas after the ground modification, maybe about 20 millivolts, really looks like at about half the 125 kHz. Offhand, that seems kind of strange. It stays looking pretty good up till about 9 amps of load, then this happens. Notice the voltage scale. Almost 20 volts of oscillation. Can't run it long like this, I smell my snubber resistor getting hot. Here a zoomed in look, nice sine wave at half the power supply switching frequency. I would have thought that reducing the feedback loop size and along with it the inductance would have caused the oscillation frequency to go up, but I guess not. I must be overlooking something. Seems strange. So this makes me think that my power supply switching noise is getting into the amp from the ground. Looks like I may have a ground problem. But on to the next test. When I eliminated this section, that stopped the convoluted oscillations in the 1 to 3 amp range. I'm going to put it back. Just a matter of removing a jumper and replacing a few resistors. I'm very curious if those strange oscillations were from the output of this amp being too close to the negative voltage rail. So I'll put everything back the way it was. I'll also remove the ground jumper on the MOSFET power module as well, and put the common ground back on the bus bar. Since I do have a negative 5 volts on the control board, I'm going to lift the negative supply pin of the op amp from the PC board. I kind of hate doing this. I only have one more of these chips, and they're still out of stock it seems. But the only way I know to tell if the problem was the output too close to the rail voltage is to supply a negative 5 volts to the op amp. I'll put a 2.2 microfarad capacitor from the negative supply pin to ground. Not great for the capacitor, but that will help support the pin of the op amp, and I'm much more concerned about that. Then I'll solder on a wire that will connect to the negative 5 volts on the control board. Okay, the OPA 2189 is now running off of a positive 12 volts and a negative 5 volts. Let's see if that was the problem. Again, this is AC coupled signal at the load terminals with the load attached to a 600 watt linear power supply. I'm at 1 amp load here. If I compare it to the waveform before the negative supply modification, this is what a 1 amp load looked like with the negative supply of the op amp at ground. All kinds of crazy stuff going on. Certainly a lot different. If I zoom in, not a lot of crazy now, just the 125 kHz power supply frequency in the mix. Around 250 millivolts in amplitude, and from the previous test, I now believe most of that is getting in from the ground layout. At 2 amps, still looking good, mostly that 125 kHz sine wave in there. This is at a 10 amp load. This looks like that when the bridge rectifier in the linear power supply is conducting, there is less amplitude of the 125 kHz sine wave. I thought it might just be the leads from the power supply to the load that are seeing the oscillation, but maybe not. I would expect that when the rectifiers are conducting, the power supply has a slightly lower impedance. That may be what I'm seeing here. At a 20 amp load here, about 4.5 volts of 120 cycle ripple now. If I zoom in, maybe 300 millivolts of the 125 kHz. This is a section of the waveform where the bridge rectifier is conducting, so on the discharge ramp it is a bit higher, but not horrible. And finally, at a 30 amp load, a little over 6 volts of 120 cycle ripple. The 125 kHz oscillation doesn't change a whole lot from 1 amp to 30. Well, I have learned something. Don't plan on using the output of an op amp near its supply rails. Now I wonder how well those OPA 364s work with the negative bias applied to the output. Now to test and see if the 125 kHz is getting in from the ground or someplace else. So for this test, I'm going to put the jumper back on to tie the source load terminal to the ground. I'll do that for both modules. And I will remove the ground lead to the bus bar. The ground setup is just like the first test. So I'm at 1 amp here, and that doesn't look good. Taking a closer look, no 125 kHz sine wave anymore, at least none that I can see. Some pretty high frequencies in there. At 2 amps here, at least it's reading 2 amps, nearly 2 volts peak to peak, so some pretty high peak currents in there. Zoom in, and well, the 125 kHz power supply frequency is gone, I would say. Let me see what frequencies I've got here. Over 600 kHz. Wow. I don't know how it's doing that. With the RC time constant at the gate of the MOSFET, I wouldn't think it could oscillate at that frequency. Maybe an interaction between the two modules? At 3 amps, almost 3 volts peak to peak, so I'm sure it's pulling well more than 3 amps. Looks like the frequency might be increasing as the current goes up. I was expecting maybe some strange things as the ground potential of the two modules differed, but I wasn't expecting this. You might be wondering where the higher current waveforms are. Well, the power supply really didn't like being subjected to this. At a little over the 4 amp reading, the power supply blew its 8 amp line fuse. Not sure why. I know the load current on the power supply wasn't near enough to blow the fuse. Maybe the high frequencies getting back to the bridge rectifier was messing up the reverse recovery time, and the rectifiers weren't able to turn off. Put a new fuse in the power supply and it's good to go. One of the good things about a tough old linear power supply. This was going to be the last test, then I was going to make a decision where to make a new power supply or new MOSFET amp modules. But this has me puzzled. I really wasn't expecting it. So I'm going to try this same test with just one module connected. Well, one module driven. The source and drain load terminals of the unused module will stay connected. That's something. With a single module, the oscillation is even worse, over 3 volts at a 1 amp load. Well, the frequency is a lot lower with the single module. Here's the waveform with the modules swapped. Frequency may be a bit higher, but it's close to the same. I'm at 1.5 amps here. Well, that's what the amp meter is reading. Looks like over 4 volts peak to peak. I'm going to stop here. Snubber resistor is starting to get warm, so I don't see any need to go any higher. The snubber is mounted right across the bus bars, so when I move the ground to the MOSFET modules, that puts about 10 inches of wire from the ground to the snubber. Is that where the oscillations are coming from? I do think I learned a bit from these tests. Those strange low current oscillations, I believe, were being caused by the OPA 2189's output being operated too close to the negative supply rail. And that really was carelessness on my part. Trying to get by without a negative supply rail wasn't a good idea. And I think the 125 kHz power supply frequency is getting in through the ground circuit. Maybe the ground wiring. I hope the ground wiring, and not the way I laid out the ground on the main control board. I'm still not sure the cause of this problem. Looks like more tests ahead. I probably will start a new power supply, isolate the fan supply from the rest of the system, and clean up the noise output. That can only help. Sometimes seems like 1 step forward and 2 steps back. I answered one of my questions, but not sure of the other one, and found a new question I need to answer. Thank you for watching.